Hey guys, Mr. Betts here. I want to talk about something called the ratio test. And the ratio test is a test that we're going to use to test whether a series converges or diverges. There are some cases where the ratio test really doesn't do anything for us, but we are going to get a lot of answers about whether a series converges or diverges. So I want to start this with looking at some geometric series. So we know that with a geometric series, first of all, a geometric series is a series that has a common ratio. So we multiply by the same thing over and over to get from one term to the next. And we also know that if the common ratio is between -1 and +1, the series is going to converge. So looking at this first example here, it is a geometric series and it has a common ratio of 1/2. So we not only know it's a geometric series, but we also know because the common ratio is 1/2, this series is going to converge. We can also, with geometric series, figure out what that sum is going to be, but we're not interested in that right now. The second one is not as obvious, but it is also a geometric series because to go from one term to the next, we're always just multiplying by x. So yes, it is a geometric series. The common ratio here is just x because we just multiply by x to get from one term to the next. And we know this one will converge under certain circumstances, specifically if x is somewhere between -1 and +1. So this is just kind of a general form for a geometric series. The last one, if we look at the ratios here, so I'm just going to take two of them to show that it's not a geometric series. If we take a look at the ratio 1/3 divided by 1/2, that's going to be 2/3. And then if we look at 1/5 divided by 1/3, that's going to be 3/5. So since these two ratios are not the same, it's not a geometric series. It actually turns out that none of these ratios will be the same, so it's not a geometric series. However, I want to point out that this series is really similar to the first one. So the first one is a geometric series, and we know it converges. And if we just look at the general term, the only difference is we're adding 1 to the denominator in the second one. And I do want to point out also that since we're adding 1 to the denominator, each term in the third series here is going to be a little bit smaller than the corresponding term in the first one. So 1/2 is less than 1. 1/3 is less than 1/2. 1/5 is less than 1/4, and so on. So just based on that, that's reasoning that we could use a comparison test with and say that since each term in this series is smaller than each term in this series, and we know that this one converges, then we could also conclude the third one does. But I want to look at how we might show this last one converges and not using a comparison test. All right, so I already answered this question. Yes, we know this one converges because the common ratio is 1/2. This one converges if x is greater than -1 and less than +1. And this one we really don't know, except based on the fact that the terms are smaller than the terms in the first one, we could assume that it's going to. So what I want to claim here is that even though this one is not a geometric series, it's going to behave like a geometric series. Specifically, it's going to behave more and more like a geometric series the further along we get. So we looked at ratios from one term to the next. So the ratio here was 2/3. The ratio here was 3/5. And then if I just keep going here, the ratio is going to be 5/9 and then 9/17. And if you look at the decimal representations of these, or if you just think about what's happening here, the numerator is getting close to half of the denominator. Since we have all odd terms here, it can't be exactly half, but each time we're getting closer and closer to a ratio of 1/2. So even though the ratio is not constant, it's getting closer and closer to a ratio of 1/2. So as that ratio gets closer and closer to 1/2, this is going to behave more and more like that geometric series that we saw that didn't have the +1 here. So formally, what we want to do is we want to show that the limit of these common ratios is actually approaching 1/2. And the way we're going to do that, I'll come back to that. The way we're going to do that is actually look at a limit. So rather than thinking of one specific term to the next, what I'm going to think of is going from the nth term to the n plus first term. So the n plus first term we would get just by plugging n plus 1 in here. And if we look at that ratio, I'm going to just say r sub n. It's the nth ratio between the n plus first term and the nth term. What we get here is going to be 2n plus 1 over 2 to the n plus 1 plus 1. All right, so if we simplify, it ends up being that. And if we look at what happens as n gets really, really big with this ratio, we're going to look at that with a limit. And we're going to have to remember some relative rates of growth, or what I called dominance earlier in the year. And in this limit, the 2 to the n is going to dominate here, and the 2 to the n plus 1 is going to dominate in the denominator. And so this is going to behave like, the limit as n approaches infinity of 2 to the n over 2 to the n plus 1, which is 1/2. So as n gets really big, this ratio between the terms is getting really close to 1/2. So then my claim is, since it's behaving like a geometric series, because each term is pretty close to 1/2 of the term before it, and the geometric series that has that as a common ratio would converge, then this series is also going to converge. So that idea gives us the ratio test. And the ratio test says if we have an infinite series and the limit of the ratio of the n plus first term divided by the nth term exists, then we can make conclusions based on what that limit is. If the ratio is less than 1, that means it's behaving like a geometric series with a common ratio less than 1, then the series is going to converge. If it's greater than 1, then it's going to diverge. The one thing that it doesn't tell us is if that ratio is approaching 1, then we don't know. The ratio test is inconclusive. Okay, so I want to point out that we do have absolute values here. That's why we're not saying -1 is less than r is less than 1. So what we're looking at here is what's called an absolute series, and I'll talk about that in a moment. But we're only going to get positive values for r since we have that absolute value there. So a few notes about it. The first is this is a test for what's called absolute convergence. So it doesn't matter if terms are positive or negative. This is a test that's going to tell us that if the terms were all positive, what would happen? So would it converge or would it diverge if the terms were all positive? That's kind of a worst case scenario, because if we have some positive and some negative, then we're going to have some canceling out, and that's going to make it more likely to converge. So if all the terms are positive and it still converges, then that tells us a little bit more information than if some are positive, some are negative, and it converges. Another thing I want to point out is that the ratio we looked at looks like this, but in order to do this, usually what's going to happen is the terms are going to be fractions. So let me go back to the example we were using here. So the general term here is a fraction. And if we're dividing fractions, it's going to be easier to multiply by the reciprocal. So generally what we're going to do to write this expression is we're going to take the n plus first term, which will be a fraction, and we're going to multiply it by the reciprocal of the nth term. So rather than dividing fractions and having a complex fraction and then dealing with the complex fraction, we'll multiply by the reciprocal right off the bat, and that's going to make things a little simpler to get started. The other thing I want to point out is that since we're looking at limits as n approaches infinity, the relative rates of growth or relative magnitudes of growth that we talked about way back in section 1.15 is going to be useful, and it might be worth going back and reviewing some of those ideas.